Good morning, everyone. Welcome to our Zoom lecture. Before we get started, I just want to bring to your attention that this past weekend I was able to fix the issue with DSM, dynamic study modules. You should be able to access or see the questions. Please do not go to the global site to access the dynamic study modules, because you'll see all the problems for each chapter. But I want you to just go through Canvas and do the assignment, as well as the dynamic study modules, which are available until the end of the semester. For chapter one, it was supposed to be due this past Sunday, but since we are not done with chapter one, I extended until this coming Sunday, because today I want to finish chapter one and get started with chapter two. Without wasting my time, let me share my screen and we will get started with the lecture. If you are not here last class meeting, we went as far as section 1.5, and we were done with 1.5 on measurement. We talk about the mass measurement, different systems of measurement, metric, English, all right, and SI. Please familiarize yourself. You should be able to distinguish. We also look at the concept of temperature and the 3 units used to express temperature measurement. Density is an important physical property you'll see quite often in chemistry. Please do practice on problems on density as well. Before we get to the concept of significant figures, you will encounter, in most science courses, you will encounter 2 types of measurement, that is exact versus inexact. What we mean by exact are those numbers obtained from counting, numbers obtained from counting are considered as exact. For example, 7 days in a week, you have to count. 4 quarters in a dollar, you have to count. 7 oranges, you have to count. And then also the definition, such as 1 dozen equals to 12 eggs, those are exact numbers. 1 liter equals to 1,000 ml, that's a definition. So equivalent statement you will encounter are also classified as exact, as opposed to inexact numbers, which have some uncertainty associated with the instrument used. This has some uncertainty, and you can identify or differentiate, distinguish exact numbers from inexact, because an instrument is used in obtaining those inexact numbers. They have degree of uncertainty, their degree of uncertainty, which I want to start from there today. Let me see if I can, my stylus pencil is not working for some reason. I have to see if I can charge, see if I can share my whiteboard. If it doesn't work, we'll try the best we can. Let me see if I can share my whiteboard so that when I give you examples, you'll be able to follow. So here is, let me see if it's going to respond. Oh, still not responding. I'll find out from the TI, rather Resource Center, if if they can switch the iPad. Nevertheless, uncertainty section 1.6, this is the section where you will see the concept of significant figures. Not all numbers you see on your calculator when you do calculation such as determination of density, you'll end up with more than the required digits in expressing the final answer in your calculation. In this section, we'll see how to express the final answer with the correct number of significant figures, which means we'll drop the last digits, which are non-significant. So here, all measured numbers have some degree of uncertainty. You'll see plus or minus in a measurement obtained using any equipment or any instrument. For example, here is a temperature measurement. We are sure that the temperature is above 20 degrees Celsius and below 30 degrees Celsius, but this 27, the last digit here, there is some degree of uncertainty. So in all measurement, it consists of certain digits and one last uncertain digit. In this case, the highlighted 7 here has a degree of uncertainty. Uncertainty. There are two terms here you will see, and this has to do with the measurement, accuracy versus precision. You may use these terms in making conclusion in your maybe lab report that your data are accurate or they are both accurate and precise. What's the difference between these two terms? Accuracy, all right, is like saying the truth. That is one time. Versus precision is saying the truth over and over. So this term right here, accuracy is the, all right, how close a single measurement in a series of measurement to the true value, Whereas precision is a measure of how close a set of data to one another. So this one compares data to data within a set, whereas accuracy compare one measurement in a set of measurement to the true value, value. So we have precision, a measure of how closely individual measurement agree to one another. There is accuracy. This refers to individual measurement to the true value, okay, to the true value. You should be able to define those terms and also have, I've seen problems on these two terms in relation to that. Maybe you'll see in the text an illustration using the dot where it talks about the precision and accuracy. This is what I mean by the dot. The first one is both accurate and precise, that if the bull right here is what is the target, all the three arrows are just in the target. You see, good precision, good accuracy. Whereas this one, even though they are close to one another, they are not accurate. The target is the eye or the bull's eye right here. A set of data could be both inaccurate or imprecise, poor accuracy, poor precision. So you need to know, you need to understand when you make a conclusion in your lab report, you may use this vocabulary, these terms in stating whether your data is accurate or precise. Well, let's shift gears to significant figures. Significant figures are the most important numbers used in expressing a measurement. And we start counting significant figures from left to right, from left to right. And there are some instances where zero do not count, where zero do count. I see common mistakes students make is when to count zero and when not to count zero. Let's see. Before we look at the calculation, we will only look at the what? We'll have to look at the rules in determining the number of significant figures before we go down to calculation and rounding of numbers. I want us to look at the rules for expressing or counting significant figures. All non-zero digits do count as significant digits. All non-zero digits do count as significant figures. So if I do have a number such as 1, 2, I don't know if I can use the annotation here, a number such as 1, 2, 3 like that. This is, these are, maybe I can put a unit here to be a measurement. All these 1, 2, and 3, we start counting from here. This is 1, 2, 3 here. They are all significant digits. So this has 3, 6. It's hard to write with my mouse. 6 figures. I can say this is 3 significant figures or 3 significant digits. So that's what you need to know with non-zero digits. Now, zeros in between non-zero digits do count as significant figures. For example, all right, for example here, 1, 0, 0, 9, 8, this should be 9, this is my 9. So if I do have here crowns, the zeros being referred as lying in between non-zero digit here, these are the 2 zeros and they do count as significant figures. So 1, 2, 3, 4, 5. This measurement here has 5 significant figures. The zeros do count. Now, there is, all right, 2 types of zeros. Trailing zeros and leading zeros. Zeros at the beginning of a number, we call these leading zeros, and they do not count as significant figures. Never, look at this, never count as significant figures. If I have a number such as 0, 0.0, 2, 5, all right, ml like that, ml, just make it a measurement. The zeros you see here do not count as significant. The zeros here, I'm just gonna cancel that, and they do not count as significant figures. Do not count. So we start counting from here, 1, 2 here. These are the 2 significant figures, 2, 6, all right, 2 significant what? 2 significant figures, 2 significant figures. We count 2 significant figures. So that's how you count what? The zeros. We call these, some others call these leading what? It's called leading zeros, leading zeros. It's lead, yeah, leading. Zeros like that. Zeros in between do not never count as that. So rule number 1, we have looked at that. Rule number 2, rule number 3 there. Let me clear this so that we move on to rule number 4, and this has to do with the zeros at the end of a number. We call these trailing zeros. It comes before. So I'm just gonna label this as trailing. It is coming, trailing. I zeros do not count as significant unless there is implied place of decimal. You see, unless there is implied place of decimal, we do not count that. So what we mean by implied place of decimal, I can have 100 like that, 100. These are, it's just coming up the non-zero digit. There is no place of decimal. We call trailing zeros. Unless there is an implied place of decimal, they do not. If it contains that place of decimal, so this one has one significant figure. But if I have a number such as 1, 0, 0, and then another 0, and then I have a place of decimal here. I have a place of decimal here, and then the zeros do count now as significant digits. So I count 1, 2, 3, 4. This has four significant figures, four significant digits, four significant digits. So you need to know these rules. I'll give you a question you'll see in the exam is just a number. How many significant figures do we have in this number? You just pick up the word. You have just to pick the correct answer. You know, I tend to, stay away from the last, especially when, if it was face to face and I print exam and maybe there was a place of decimal. Sometimes maybe they might not be visible. And somebody will say, I didn't see place of decimal. So the first three here. Any question on the rules of significant figures? Any question? There's no question. Let's move on to calculation. We'll see or before we look at that, when these numbers, or rather zeros at the end, we use scientific notation to take care of numbers at the end to see if it has or if it includes. These are the numbers in scientific notation, and anything on the left side of the multiplication sign. You see this multiplication sign, multiplication sign, multiplication. Anything on the left side do count as significant digit. Do not let the exponent here confuse you. You see exponent for all of them, but if you count these 1, 2, 3, three significant figures. 1, 2, 3, 4, four significant. 1, 2, 3, 4, 5. 5 significant figures. All right. So that's how you take care of those numbers at the end. So let's see if you, Nicholas, I see. Oh, yeah, I guess I took care of that. Nick, thank you. Thank you, Ada. So somebody's saying I make the, all right, I'm just gonna make this large. Somebody say make it large. All right, sorry about that. I was hoping to share my whiteboard, but I'm just gonna share in a minute. I guess I had to charge my pencil so that I can show examples on this. So, Ada, is that fine? Just say yes down there. Are we together, Ada? Is that fine? Thank you. All right, let me just put that down there. Thank you. So these are the problems you will encounter, you come across in a quiz or exam. What is the number of significant digits in the following? The zeros here do count. 1, 2, 3, 4, 4 significant digits. 1, 2, 3, 4, 5, 5 significant digits. And here 1, 2, 3, 4, 5, 6, 6 significant digits. Just, with practice, you nail it down. This is maths, it's a concept you need to know. I don't know if I cut your question, Catherine. Do we have a Discord for this class? A Discord, I don't understand what you mean by Discord. Can you explain one more time, Catherine, please? Oh, yeah. Yes. Thank you, Nick. They screwed me. I guess maybe it's some app or a website or somewhere people can post. So please, if you can see Nick's or DM Nicholas, Catherine DM Nicholas, and he will take it from there. Thank you. So that is how you encounter this. Please do not rely heavily on PowerPoint slide thinking that you will ace the exam or quiz. This is just to give you the concept. Yours is to go out there, look at several problems, and if you look at the end of chapter problems, I think odd numbers, the red numbered one have answers at the end of the book. So please practice with that. So let's look at the significant figures and calculation. Allow me to see if my whiteboard is my pencil is now responding to whiteboard because calculation may be showing you examples. So let me see if yeah, it works now. We're in shape, but I need to minimize now. Since that is good enough, I'm just gonna have this right here. So calculation, we're not gonna go into crazy calculation, quadratic equation, not at this time. But I will split calculation into two. I'll split calculation into two. Group into addition and subtraction, and then multiplication and division, like that, which summarize the rules for calculation. Here, I will look at the what? Least, you can write your own notes or own statement, least number of least number of decimal places. I'm gonna look at the least number of places of decimal wherever I'm expressing my final answer. If I do have a number such as 10.1 plus 2.21, let me just get rid of that. This has one decimal place. This has two decimal place. As far as my statement here is concerned, the one with the least number of places of decimal determine how many places of decimal your final answer should have. Not significant digits. It is number of places of decimal. So this one has 1 versus 2. So the final answer should have one decimal place. So this is 12.31. You'll see this on your calculator, and it does not mean it is correct. It does not mean it is correct, right? That is not what we are looking for. It is something you need to remember, that it's place of decimal. So I'm just gonna stop here. All right. And the final answer should be 12.3. 12.3. Please pay attention to rounding off. I know there was rounding off. If this number right here, was greater or equals to 5, And then we say that the, all right, we say that the measurement, or we increase the preceding pi 1. We increase the preceding pi 1. Let me sync one more time. My whiteboard is not syncing. Maybe new record. And so if this is greater than 5, all right, if this is greater than 5, you increase the preceding pi 1. You increase the preceding pi 1. You increase the preceding pi 1. So that's how you have the uh, final answer for calculation. Hold on a second, hold on a second. Sorry about that. So that is the addition, subtraction, addition, subtraction. If we are adding, subtracting, you look at the least number of significant number of places of decimal. I'm gonna be looking at the places of decimal in, I'm gonna be looking at the places of decimal in subtraction and addition, so that you express the final answer with the new least number of places of decimal. Note the number of appropriate, so you have to round off. If you have to round off, you'll have to do that. For multiplication, it is the significant. Yes, somebody is ahead of the slide, that when you're looking at the multiplication, you look at the least number of places of decimal. I guess it's coming for that, so that if I know for multiplication, you look at the you look at the you will have to look at the least places of decimal. If I'm looking at multiplication, you have to look at the which one has the least number of places of decimal. Is failing to pick up my whiteboard, but nevertheless, if I'm looking at multiplication, let's see, before we look at this example, how do you account for multiplication? For example, 1.2 times 2, all right? 1.2 times 2. If you look at these, I'll count these as what? Two significant figures. This has one significant figure, and then the final answer will have one significant figure. If you have 2.3, 3, For count the significant figures, time is 2.8. I'm just giving you examples without giving the final answer. This has 1, 2, 3, 4, four significant digits. This has 1, 2, all right? This should be, I meant to say 8. I'm gonna have that, we'll have this 2.8. 4 versus what? 4 versus 2. So this has 4 significant figures here, and this has 2. The final answer should have 2 significant digits, 2 significant digits. So I look at that, and this applies for what? Multiplication. This is multiplication, multiplying and dividing, multiplying and dividing, so that you have to know that. I know I showed you the addition, so that for this example here, you look at the what? The places of decimal. This is 14.3505 plus 2.65. This has 2 places of decimal. This has 1, 2, 3, 4. So your final answer here should have 2 places of decimal because of 2 here. This is 2, this is 4. And remember the rounding off. Remember the rounding off plays a role in the calculation. So this is equals to. And then here, these do not count. Remember how we count the significant figures? It defaults now under addition, multiplication and division. And the one with the least significant figures will determine how many significant figures we will have in the final answer. This has 1, 2, 3. The 0 here do not count 1, 2, 3. So it doesn't really matter which one we are using to determine the number of significant figures in the final answer. But, all right, but we will use the either of them. If this has 2, then the final answer will have 2 significant. That's what I wanted to mention before we go to dimensional analysis. Before we go to dimensional analysis. Any question on the significant figures and calculation? Yes. Quiz number 1 will be on chapter 1. Clark, yes, it will be on chapter 1, which we are going to wrap up in a minute. We are going to wrap up in a minute, chapter 1. Once we go through dimensional analysis. Yes, Player Nelson does the same decimal. No, decimal places is only for addition and subtraction. How many places of decimal? The one with the least place of decimal? Come on, how many places of decimal? We do not look at the place of decimal in multiplication and division. We only look at the significant figures. Thank you. Thank you for that. Now, dimensional analysis, we always use this. It's a powerful way. It's a powerful method of solving problems. In most of the problems you'll encounter, you'll use the either factor label method or dimensional analysis. This is sometimes called factor label method, which is used in converting unit of measurement from one unit to another unit by deriving what we call conversion factor, by deriving what we call conversion factor. I'm still trying to see if I can synchronize my whiteboard with the iPad, show you how factor label method works. Factor label method works. Let me try one more time, see if it will pick new, and no, it doesn't work. Let's see, right here. So factor label method is the same as dimensional analysis. It's the same as dimensional analysis. We call this factor label method, which is used in converting unit of measurement from one unit to another unit. For example, if you are asked or if you are given an equivalent statement that 1 inch equals to, I don't know why it's going back again, shouldn't refer back to. So if I have 1 inch here, let's try a notation, 1 inch equals to 2 point what, 2.54, for example, here 2.54 centimeters. This is an equivalent statement. This is an equivalent statement. You will need to convert from inches to centimeters or centimeters to inches. And in this case, dimensional analysis will be handy. You know, you have used this changing from grams to kilogram, from kilogram to grams, from miles to kilometers, from millimeters to centimeters, and so forth. We make use of dimensional analysis, dimensional analysis. So this is a technique used in changing system of measurement or one unit of measurement to another unit by using the what? The conversion factor. Conversion factor is derived from the equivalent statement. We call this equivalent statement. But if I have 1 inch, all right, if I have 1 inch here, 1 inch at the top, and at the bottom here is 2.1, 2.5, 2.54, 2.54 centimeters. I've derived the conversion factor. This is something you'll have to generate if given something. This is centimeters right here. If you are given this in exam or you are expected to know, you have to generate a conversion factor so that you change a given unit of measurement from unit 1 to unit 2 using a conversion factor. So conversion factor is just a ratio of two measurement. Using this one, we can derive the conversion factor between two units. This is an example, this is an example of a conversion factor. When you do that, please do not just put in the numbers. Common mistake I see, student, if you don't put the units so that you cancel out the units the way you cancel the numbers, you may end up making a mistake in setting up your problem in conversion or in dimensional analysis. So it's a simple way of which if you are given unit 1 and you are asked to convert to unit 2, we generate a conversion factor. If you have unit 1 and you are asked to go to unit 2, you use a conversion factor. So these are conversion factors, and the flow chart, the roadmap you see here constitute what we call dimensional analysis. I know you have used this before. Let's see. If you are given a number such as this is 5.00 days to seconds, how are you going to go about with that? First, final answer should have three significant figures. 5.003 significant. You have to convert to seconds. It's not always that it's going to be true that you have only one conversion factor for every dimensional analysis you are expected to carry on or to perform. You may need to use multiple conversion factors in order to arrive at the final answer or to express your final answer with the correct number of units. So in this case, we may move from days to hours, from hours to minutes, and then from minutes to seconds. So you'll have to generate your own what? Your own conversion factor, understanding that 1 hour, all right, 1 hour equals to what? Equals to 20 what? 24, uh, 1 hour equals to 60. Or maybe in a day, we can start with days. If we start with that and say 1 day like that, 1 day equals to what? Equals to 24 hours, so that you change from hours to seconds. And then 1 hour, all right, 1 hour equals to 36, 0, this is 36, 0, 0 second like that. So that you now write your what you are given, so that you cancel out 5 point 0 0 days. All right, so if I put a day there, multiply pi, this is day. I want to cancel day here and go to hours right there. That means you'll have to plug in the numbers from the equivalent statement. You know how to go about with this. And then time is what? Time is, you want to remain with now seconds here. So 36, 0, 0 seconds over 1 hour, so that you cancel out day and day, you cancel out hour, this is hour, there, cancel that. And then you multiply everything at the top and you divide by that. That will give you the final answer. What we have used here is dimensional analysis, factor label method. You can do the same thing for B, miles to meters. You will need, right? If this was my lab mastering chemistry assignment, they expect you that you have the text or any other resource to look for equivalent statement you can relate between miles and what? And meters. Between miles and meters. You can say how many miles. 1 mile equals to 1.62 kilometers, and then 1 kilometer equals to 1,000 meters, and then you do the same setup and express your final answer with the correct number of significant figures. So that's how you use the factor label method. For the remainder, for most calculation you will encounter even in chapter 10, 7, you'll make use of the conversion of factors derived from the equivalent statement. Any question on factor label method? All right, I'll make them available, Ragada. I'll make them available, the lecture recording from the first day. I'll enable them so that you can see. I'll make the previous lecture recording and post announcement with that effect. Thank you for bringing that to my attention. Let's see, I meant to clear this. Let's clear this first. All right. Any question on chapter 1, please? Any question? Please practice with end of chapter problems, the temperature conversion, calculation of density, and using the factor label method. I will not spend more time on chapter 1. I just want to shift gears to chapter 2. Please take note of the due date for chapter 1 assignment. I extended the due date until Sunday, simply because we are not covered the factor label method, the significant figures. You can still go back and complete that. that marks the end of chapter 1. Let me see if I can try one more time synchronizing my iPad with the with the laptop Mac. So I'm trying to synchronize simply because I'll be giving you examples, and I want to give examples as much as I can. See that. So let's shift gears to chapter 2, the ions, and hopefully let me enlighten this, make sure we look at that. And by the way, the PowerPoint slides you see here, they are posted on, I do have them on Canvas. Chapter 2, I will post a quiz on chapter 1 tonight. Tomorrow it will be available. So chapter 2 is on molecules, atoms, and ions. You have seen these terms before, all right? I know you have encountered the terms you see here before, but I'm just going to go through real quick on what they mean. The ions, molecules, and atoms. What do they really mean? How do we end up with this? Atom is a term coined from the Greek term atomos. This is a term coined from the Greek term atomos, which means the smallest indivisible part of matter. This term atom is derived from the Greek term atomos, which means indestructible, indivisible part of matter. Initially, in the day, there were two schools of thought. How did we end up with this term, or how did they end up with the term indestructible? Democritus was a Greek philosopher, believed that matter can be divided into a dead end. That means if I have a small piece of paper, right? This is a small piece of paper. If I tear it into two, how long will I go tearing this? You see this? I'll keep on and on and on and on. And he argued out that the end, the smallest indestructible part of matter is an atom, which, you know, Plato and Aristotle believed that you could go on and on and on indefinitely. We will look at the molecules, and in particular, you know, when you put together the non-metals in a specific divine ratio, they end up with molecules. We will look at the ions later, ions, which is simply the charged particles, can be cation, it can be anion, cation or anion. So let's see. The first approach into looking at the atomic theory started with Democritus, which believed that matter can be divided to a point where you can no longer destroy it. Democritus believed that the smallest indestructible part of matter is an atomos. I'm not going to ask you what is atomos, but it's good to understand how did we end up with this. Now, fast forward, this is way back, fast forward to around 1800, John Dalton, which I believe you have heard about Dalton's theory, based on the observation, there was some observation, experimental observation around 1800, which people could not explain until John tried to explain that. For example, you see the law of mass conservation, you know the law of mass conservation. Matter cannot be what? Created or destroyed. Everybody can recite that. It's pretty straightforward. How? It's because of the fact that in a chemical reaction, it is the rearrangement of atoms. You do not destroy atoms. You just take this, form this. And Dalton used that observation of low mass conservation to explain that there is the fundamental building block of matter. These were the observation which they could not explain until Dalton now tried to explain his atomic theory based on the law of constant composition, law of mass conservation, and law of multiple proportion. Please make note of, I know in the text they explain it, this has been broken down. You should be able to differentiate those laws. Law of constant composition, which says that compounds have definite composition. What does this mean? H2O will always be H2O. It has a definite composition, whether it means Canada, Australia, Mexico, big two countries, constant composition because of the atoms. Law of mass conservation, all right, states that matter cannot be created or destroyed, total mass of a substance. The reagent you start with should always be the same as the end results. There is an experiment, I believe experiment number 5. If you are taking the lab currently, it addresses this, or you'll demonstrate the law of mass conservation. And why is mass being conserved during a chemical reaction? Because of what? Matter cannot be created or destroyed. You do not destroy what? Atoms. All you need to do is just rearranging the atoms. This was by Antoine. And by the way, you know, these terms, I want you also to reconcile the scientist who is credited for all these scientific theories, all right? Antoine is credited for the law of mass conservation, working with calcium carbonate. Every time he decomposes calcium carbonate, he ended up with equal amount of mass, law of mass conservation. This is based on the fact that matter cannot be created or destroyed, and it has to do with the atom. So all these 3 laws, law of multiple proportion, law of definite composition, Dalton used to propose his atomic theory. All right, and these are the 4 postulates of atomic theory. You know, when we say a theory, something we cannot in reality, he didn't come up with. By the way, he didn't come up with, you know, an elaborate experiment which actually demonstrated, or he didn't come up with the actual atom and say, hey, look here, here is the atom, but he postulated what it really looked like. So they could see the law of mass conservation, but why? Or This is why I explained the law of mass conservation, law of definite composition or constant composition, that each element, which element are on the periodic table, each element on the periodic table, uh, I see students sometimes they don't differentiate between a substance, an element, a compound, an atom, and they all they say you can use interchangeably, or even matter. They say matter is the same as element. It's the same. No, elements on the periodic table have unique atoms. Here he called it extremely small, indestructible. And here are his postulate, which two of them actually are no longer valid. For example, what do I mean by no longer valid? When I say, look at postulate number 2, that all atoms of a given element are identical. They are not identical. We will see isotopes. We're going to talk about isotopes. Atoms of the same element, but they have different properties. He thought that these were the smallest, but we have subatomic particles. I know you know protons, we're going to talk about that. So this is not the smallest. We have subatomic particles, which even smaller than the atom itself. Or in other words, protons, neutrons, and electrons make up what? Make up the atom. All right. All right, somebody is asking a question about which one are we expected to put on a quiz. If it was 3 significant figures, you kind of go with the significant figures. If you're referring to the previous question, I'll go back and see how many significant figures we have that. So here are the 4 postulate which constitute Dalton's atomic theory. Each element is composed of extremely small particles we call atoms, an atom of oxygen, atom of potassium, and so forth, all those elements on the periodic table. And they are different from element to element, element to element. What do I mean by that? If we have an element, sodium, all right, they are different. Different atoms combine with atoms of other elements to form compounds. We will talk about the compounds later, so you need to know that. This is no longer valid. As I said, all atoms of a given element are identical to one another in terms of mass. It's not true. That's a pattern, but what we know, we do have what we call isotopes, which are atoms of the same element having different number of neutrons and different mass number, but that is what he postulated. So the reason why I like this, because it is no longer what? It is no longer valid. But the first one is valid. This is no longer valid. This is still valid. Atoms of an element are not changed into. There were, back in the day, people, they call themselves alchemists, those who believe that they could change elements to form pure coal, but those were just, but you cannot change atoms of an element to form another element, cannot change for that. Atoms of more than one element combine to form compounds. Of course, that's how it forms. H2O, for example, hydrogen and oxygen combine to form a compound. When we combine atoms of different elements, they form compounds. Now, let's see. The reason why this postulate number 2 is no longer valid is because we have what we call subatomic particles. And subatomic particles here are protons, which I could use my whiteboard here to show you the notation moving forward. Notation moving forward, if I do have protons, electrons, and neutron. Look at what I'm writing down, the subatomic particles. Subatomic particles, they have charges, and we have that charge, neutrons, electrons, right? They are positively charged for proton, for this proton. These are electron, it's going back again, and these are neutrons. These are neutron. Right? It is dropping my whiteboard again. I wanted to make sure you see the notation for subatomic particles, protons, neutrons, and electrons. So these neutrons. And the subatomic particles, the Dalton's view based on that, we'll see how each one of them was discovered. Neutrons, protons, please take note of their charges as well. These constitute, this makes up the atoms, neutrons, protons, and neutron. And in the atoms, where they are located, having said that, we use, or chemists use circles to indicate it's not perfect sphere. I wanted to show exact. If I have this as my atom, neutrons and protons are located in a dense region we call the nucleus. So I'm just gonna have this inside a dense region we call nucleus. So this term right here, nucleus, is the dense region where we have the protons, neutrons, and electrons are located outside. I know you have seen this illustration. How did they end up with all these, knowing that they are inside, they are outside? Different scientists made contribution towards the atomic model, which you need to know how they are, or how they went about discovering each subatomic particles. Before this discovery of an electron, this is just explanation of the cathode ray and how electron was discovered by J.J. Thomson, and how he came up with explanation on his model of an atom. Discovered electron based on the deflection. I will not ask you about, the mass of an electron, but J.J. Thomson discovered for, is attributed, J.J. Thomson is credited for discovering the electron. But the mass of an electron was determined much later by taking into account the charge to mass ratio, what is popularly known as Millikan experiment. This experiment led to the determination of the mass of an electron, which down the line you may see that. So up to that point, take-home message is, who is credited with the discovery of an electron? J.J. Thomson discovered an electron. Of course, the mass of an electron. Looking at the, remember, electrons are negatively charged. Looking at the protons now, which are positively charged, we need to understand, first of all, the radioactivity. In order to determine the position or the location of protons in an atom, Ernest Rutherford, okay? Ernest Rutherford used alpha radiation to bombard the atoms of cold, and he came up with what we call the nuclear model of an atom. But before that, somebody else by the name Pacal was studying radiation, and he was just studying the radioactivity emission of radiation, which consists of alpha particles, beta particles, and gamma radiation. This is what he was just doing. And this led to, all right, what Thomson used in his model of an atom, okay? Ernest Rutherford bombarded the nucleus of cold, the atom of cold, and he realized that most of the gamma radiation went through except few which bounced back, and it was mind-boggling for them that why is it that it is coming back? They use an analogy of using a bullet, like shooting a bullet on a piece of paper and it's bouncing back. These are positively charged, and the alpha particles, which are positively charged, bounce back because positive and positive from the classical physics, positive and positive do what? Do repel. And because these are positively charged, we have positive what? Protons in the nucleus of cold atom. We call those, see, the positive charges interacted with the positive particles, and it bounced back because of positive and positive could not. So using the Plum-Barting model, the positive when interact with that either get deflected or it bounce back. It bounce back. Remember, these are positive charge. So the bouncing back or getting deflated is because of the protons in the nucleus. This led, all right, this led to the nuclear atom. And with that, it revolutionized what you see here, Plum-Barting model right here. This is J. Thomson model of an atom that it was just as fair with homogeneous distribution of negatively charged electron and positively charged protons. But upon Rutherford experiment, cold foil experiment, the atom is modified to form what we call the nuclear atom. And in that, we have a dense region here we call the nucleus. And you know what they're in the nucleus, right? In the nucleus, we have the protons, we have the neutrons. This deflection here is because of the protons in the nucleus. We have protons here. And with that, there is diagram here, which now you have seen before, all right? That this is an atom. Could be for any element. And there is a dense region here, which we have protons and neutrons. Please take note of these two subatomic particles, protons and neutrons. They are in the nucleus, where electrons are outside the nucleus. I don't think, in my exam, I'll not ask you what is the dimension of, what is the dimension of approximate dimension of an atom? And you say, oh, in the new case, no, it's not that way. I'm not going to ask you. By the way, this angstrom here, I know you may not be familiar with it, but we can relate later on. 1 angstrom equals to 1.0 times 10 raised to 10 10 meters. 1.0 times 10 to the 10 meters, just to know. If you want to change to millimeters, picometers, and so forth, 1 angstrom. They use this term right here, calculated that. So to this point, look at the nuclear model of an atom. Nuclear model of an atom is different from the Plum-Barting model. Nuclear model of an atom, Ernest Rutherford from New Zealand is credited for that. Plum-Barting model, J.K. Thomson. Use index card to tag the scientist with their model of an atom. This is Rutherford model of an atom. And by now, you should know where the neutrons are, where the protons are. It is now different from the Dalton's atomic theory. So there are three models, or there are three ways of looking at the atom. There's Dalton's atomic theory, which he didn't come up with a pictorial representation of model of an atom, and then J.K. Thomson, and then Ernest Rutherford. We call this nuclear model of an atom. Nuclear model of an atom. No, what constitute the nucleus? We're gonna see that later on. So this is the Rutherford nuclear. Most of the, just you say that the dense region here is called the nucleus, but this is just an empty space. Outside, we have a small region we call the nucleus. I'm not going to ask you the dimension, as I said, but the subatomic particles in the nucleus are protons and neutrons. Please note also the charges. I used before positive, negative, and neutral. These are 0 for neutral. I'll not ask you for subatomic particles, but if you look at the two AMU, that is used up to express the relative mass of these charges. Any question on subatomic particles? If there's no question, take home from here we have 3 subatomic particles, note their charges, note their location, and as well as their relative masses. We'll make use of those down the line. Let's go back to the periodic table. I know you know how to read the periodic table, all right? The atomic number on the periodic table indicates the position, numbering from left to right. And turns out that the atomic number, the position on the periodic table, corresponds to the number of protons. Number of protons, I meant to say number of protons. If I go back to that, the number of protons. So if you know the atomic number, you know the number of protons. Please reconcile those two, tack those two, that you don't need to memorize the number of protons for each element on the periodic table. If I know the position, that is the number of protons, the atomic number equals to the number of protons. And of course, for a neutral atom, the number of protons equals to the number of what? Number of electrons. So if we have, for example, here, if this is an atom of sodium, let's say sodium here. If we have sodium, it is number 11. That means we have 11 what? We have 11 protons, and in the nucleus, sorry about my piece note, this is protons, and then we have 11 what? 11 electrons. This is what? This is a neutral atom. That means we have equal, no overall charge. We're going to talk about the atoms, we're going to talk about the ion or charged particles down the line. Bear in mind that neutral atom have equal number of what? Equal number of protons as well as number of electrons. Now, this is not the way you will see on the periodic table. On the periodic table, where we are going with this is the subatomic particle. If I do have, on the periodic table, we may have this right here, carbon, and then maybe 12.01, and then at the top you have 6 right there. This is off the periodic table. I'm just giving you how to or interpret the numbers you see. What you see here is representing an isotope. An isotope is an atom of a particular element with different mass number. And this is the notation. This is the difference. I'm writing this. If you look at that, what I have, it's just like below and above. Below and above. You'll never see this on the periodic table. So it is understood that, look at the notation here. It is understood that right here, this is the chemical symbol. It could be for anything. It could be for hydrogen. I can have one here, and I can have one there. I can have another one here, and I can have one there. I can have two there. I can have another one here, and have one there, and have three there. These are isotopes of element hydrogen having different mass number. Different mass number. A is always the mass number, is given by, this is an equation just such as density, mass number protons, all right, like that, plus what? These are neutrons like that. This is how you interpret this. And this is the same as the position, atomic number. Remember what we said earlier on? That atomic number equals to the mass number. So this is number one is the same thing. But why is this mass number here different? Because if atomic number here or number of protons is the same as the atomic number, that means the only difference is the number of neutrons. This conveys information you need in calculating the subatomic particle. So if I look at this is an isotope of element carbon. These are 3 isotopes of hydrogen. We have isotopes do not have their own, they do not have their own, all right? They do not have their own names, but they go with the mass number. We call these carbon 12, we call carbon 12, carbon 13, carbon 14, and so forth. So we have an element represented by 2 letters and a symbol with that. We call that an isotope. Mass number. So it's different from the position on the periodic table. I've defined these are atoms of same element with different mass number. Remember what I said about postulate number 2 for Dalton, that it's not true. He thought that, atoms of the same element look the same, but it does not look the same in the sense that we have atoms of the same element differing in number of neutrons, and in the end, the mass number also will be different. So 2 ways you can define an isotope, either using the mass number or using the number of neutrons. You can define an isotope, or you can define isotopes using mass number or using the number of neutrons. Do not confuse the mass number from the atomic mass. Atomic mass you can get off the periodic table if it is for an element, or you can use the periodic table to find the atomic mass, which we will look at it later on. But before we get to that, let's see. Here are isotopes of, 3 isotopes of element carbon. If you look at the notation, the superscript, and it is written on this side, it stands for the mass number. That is the rule of thumb. It will never change. So it is understood. If I look at the chemical symbol, using the periodic table, I know it is position 6. So position 6 means I have 6 protons. That's how you look at that. So you may not be given the atomic number, but with the periodic table, you can figure it out the position and say, all right, I know the position on the periodic table. That means I know the number of protons. From there, you can find the number of neutrons. 11 minus 6 is 5. Remember what I said earlier on, the notation here. If you need to know what is going on with this table, it is using this equation that A is mass number, which is obtained from what? It is obtained from number of what? Number of protons, like that. All right. Number of protons plus number of neutrons. So if I know the number of protons based on the atomic number, mass number minus this gives me 5, 12 minus 6 gives me that, 13 minus 6 gives me 7, all right? And maybe you are asked to fill in here. I don't know, maybe something was missing. Let's see. If I click this, it should keep fill in that. So that's what I want to show you using this equation. You can nail this, may give you in exam that this is the equation. Either you are given this and you are asked to find either that or that. That's the exercise or problems you will encounter in calculating subatomic particles. So this is 14 minus 6 is 8. 14 minus 6 is 8. I will not, I don't want to spend time on this, but we can real quick give you an idea on how to go about. By the way, from chapter 1, you should be able to name the element on the periodic table, given the symbol. So first for us, you should be able to know the chemical symbol. It is number what? On the periodic table, it is number 15. Yes, it is number 15. So if you know 15, it's the atomic number. This number, by the way, given the chemical symbol such as this, a hyphen and a number, chemical name and a number, the number at the end stands for the mass number. This is mass number. I'm gonna say this is what? Mass. This is mass, mass number, like that. Or if you want, this is A, which is the same as what? You know from the previous equation, number of what? Number of protons is number of protons plus number of what? Number of neutrons, like that. So if I rewrite that, I know you may expect to see something like that. You can rewrite so that you see this is 32 at the top right there. If you write that, and then this is 15, you are expected to know that mass number equals to, somebody has a question, let me see. I'm gonna come back to that. So you will multiply, you will subtract 32 minus 15, 17. indicate the number of protons. Number of protons is 15. Number of neutrons, you subtract that. So when you are given a symbol like this with the periodic table, this is the mass number. I am not giving you that. So you do the same thing with this. Please have the periodic table. You can look at that. Let me clear this and look at the chat window. Somebody may have a question here. All right, Jason. Yes, I'll give you the periodic table in the quiz, in the exam, all right? You don't need to memorize. I'll give you the periodic table. Well, noble gases. You see argon here, yes. You had a question about, look at the problem. I didn't mean to do that, but here is the one with the noble gas. You see, this is argon, which is a noble gas. And it is number what? Neon 10, 18, right? So you'll see that. See that? I hope I answered your question, Jason. So that's how you look at it. I'll give you the periodic table. Yours is to know, to learn. Somebody will get confused. How do I find zinc? Well, it depends on, if I look at the question, Jason, if I have a question in the problem saying that which one of the following is a noble gas, I will not allow you, or I'll not give you the periodic table where noble gases are being labeled, all right? What I mean by that is you need to know, like we're gonna look at it later on that this is group 1, this is group 2. So if I have the periodic table with group 2 labeled as group 2, or alkali metal is right here, just to give you an example, So I expect you to know, which you already know, that what are noble gases. So I know you know a little bit about noble gases, group 8. But somebody doesn't know noble gases, they'll be like, what's noble gases? Those are the elements on the last column on the periodic table. We're gonna talk about the groups. We're gonna talk about the groups in a moment. Now, AMU, atomic mass unit. It is a relative unit used by chemists to, express the mass of these subatomic particles. You can relate to a mole. 1 mole represents Avogadro number of things, okay? 1 mole. Or if I say a team of players, this is a unit. So this AMU, you may relate to, just to give you an example, you may relate to 1 AMU, atomic mass unit. Atomic AMU, first of all, stands for atomic mass unit, is 1.6, this is 6, I meant to say 6, times 10 raised to what? 10 raised to 24 grams. This is negative. That means you have to write so many zeros before you get to this number. So many zeros before you get to this number, which they are conveniently used by saying 1 AMU, and you have the mass in AMU. So it is a significantly small number that when we say 2 AMU, you know what we are talking about. Just like Avogadro or 1 mole. If we write 1 mole, that means there will be so many zeros. So atomic mass unit is a unit used in expressing the masses of the subatomic particles we talked about. And it has no relationship with the, what we have on the periodic table, in the sense that the numbers you see on the periodic table, if you have 1 atom of sodium, for example, 1 atom of sodium, weigh exact numerical value you will see on the atomic mass of sodium, but the unit will be in AMU. I know sometimes you see AMU, same number, and you're wondering what is it? If you have one sodium atom, it will weigh exact numerical value you see on the atomic mass of sodium on the periodic table, but the unit is in AMU. But if you have 1 mole of sodium atoms, it will weigh now the numerical value, but it is in grams. So to relate AMU with the grams, look at what we have. -22 is a small number. I will not really, this is what I was giving you earlier on, that 1 AMU, we use that. I'm not going to go and ask you, but just in case you see in end of chapter, maybe it will pop out. In my lab and mastering, you can use this conversion factor, of course, dimensional analysis from unit grams. Let's see how to calculate now the weight. What do we mean by atomic weight? Atomic weight here, right? Atomic weight, if I have here, I mean to, let me just write here. On the periodic table, I will use again carbon. And what you see is element carbon. This is the chemical symbol. And poloid is a number, 12.01. And this is 6 right here. This stands for the atomic number. This is an atomic what? Atomic number. And this stands for atomic what? Atomic weight. This is, I meant to say, atomic weight, which is the subject of discussion in section 2.4. How do we calculate this? I know you have not covered this. All you have to do before is just take the number and then read from the periodic table. This number here below and all other atomic masses are calculated based on the number of naturally occurring isotopes. It is accounting for all the naturally occurring isotopes, and they do not contribute towards the overall weight. If you look at the atomic masses on the periodic table, all of them have places of decimal. Why? Because of the isotopes. And there is a way they calculated that. If an element doesn't have isotopes, such as technetium, I think number 43, if you look at number 43, with the parentheses 98, that means it doesn't have isotopes. So how do we calculate the atomic weight of element? There is an equation which I want you to memorize and learn how to use that equation in calculating the atomic weight of element using the weighted averages. This is the equation. This is the equation. It's the summation. Look at this. This is a Greek symbol, means summation of isotopic mass, all right, in mu, times the fractional natural abundance for all isotopes. So remember what I say, that the atomic masses of element on the periodic table are what? Are calculated based on all naturally occurring isotopes. Silicon, for example, number 14 has 10 isotopes. And the atomic mass of isotope, they did that. So you're gonna have that. And the fractional here You are given in percent, but you are supposed to use, if you have 98, this one is masses, you will given in mass, but the fractional here, you need to change to percent. If you are given 98, let me give you an example, 98 percent, this is the same as 98 over what? Over 100, like that, which is the same as here. This is 0.98. You will use this last one. This is what you need to use. This is what you need to use in this equation. This equation right here, you need to use fractional. This is what we will have to, not the 98. If you plug 98%, you end up with the wrong answer. You'll end up with the wrong answer. So what I want to plug in here is maybe using one example, show you how the atomic weight of all elements on the periodic table are being calculated using the equation and their naturally existing isotopes. Carbon 12, carbon 13, carbon 14. This is an example on how to calculate the atomic weight of copper using two naturally occurring isotopes. This is copper 63 and copper 65. For copper 63, this is an isotope with mass number 63. This is the mass in AMU, percent abundance. So we'll change this point what? 0.07215 times 62.9296 plus, remember the summation. So change these two places of decimal, 72.15 over 100 is the same as 0.72 times this. Then for copper 65, this is its isotopic mass in AMU. We change this to what? To places of decimal as well. The summation sign here means you add all of them depending on how many we have. So if we add 4 of them, we'll have keep on adding. If we add 5, we'll have add. Remember to change these two places to decimal notation. One thing I've noticed is you may be given, if the element has 3 isotopes, you may be given percent of the 2, but not the percent of the third one. So you have to do the math and say, if I have to, add the percent of the 2 and then subtract from 100%. What I'm trying to say is percent abundance should always add up to 100%. If it's 100.001, it's okay. If it is 99.99, it's okay. The point here is if you have 2 isotopes, you are given percent of one, you are not given the percent of the other one, you have to do the math and then do the calculation. So that's what you will need to do for calculation of atomic weight of our element. I don't want to continue from here. I want to stop from here, and it is now 12:29. The class is dismissed if there is no question. I'll see you again on Thursday. I'll make the PowerPoint slide available. Somebody asked during the course of the lecture, and also the quiz for chapter 1. Please continue reading and doing the homework assignment. The class is dismissed. Thank you. Hopefully you will make use of the tutorial session. Please see Nick, he posted the meeting time, the schedule this morning. Take note of that as well. Thank you. See you on Thursday, same time. Start reading chapter 3, please. Start reading chapter 3.
Thank you.
Thank you.